At the quiet centre of a distant galaxy called NGC 3842 lies one of the heaviest known black holes in the nearby universe, a supermassive giant weighing billions of times more than the Sun. Its gravity dominates not just its galaxy, but a whole region of space swallowing stars and steering the motion of everything around it. Today we explore what its true scale really means, and how it compares to other cosmic monsters across the universe. If you enjoy calm journeys into extremes like this, please subscribe and share, and tell us in the comments, what would you most like to know about a black hole this massive? Thank you for watching. Now, let's begin. On the largest scales that current observations can map, the matter in the observable universe is not arranged uniformly but forms an extended network of concentrations and underdense regions. Galaxy redshift surveys that measure distances for hundreds of thousands or millions of galaxies show that these systems gather into elongated filaments, flattened sheets, and dense knots with vast voids occupying the spaces in between. This pattern arises in standard cosmological models from small differences in density in the early universe, amplified over time by the pull of gravity, with dark matter acting as the main framework on which ordinary matter collects. The result, seen over distances of hundreds of millions of light-years, is a structure in which clusters of galaxies sit at the intersections of filaments. Superclusters extend across large volumes, and empty regions span tens of millions of light-years with very few galaxies. At these scales, astronomers treat the universe as statistically homogeneous and isotropic, meaning that on average it looks the same in every direction and at every location when large enough regions are considered. This statistical regularity does not remove individual concentrations. Instead, it provides a framework in which features such as galaxy clusters and superclusters can be described as typical fluctuations around an average density. Numerical simulations of structure formation follow the growth of these fluctuations from shortly after the Big Bang, evolving a mixture of dark matter and ordinary matter under gravity and cosmic expansion. When these simulations are compared with wide field surveys that measure galaxy positions and the hot gas between them, the match between theory and observation shows that the large-scale pattern of filaments, walls, and voids is a natural outcome of the current cosmological model. Within this network, matter flows slowly along filaments toward the dense regions where clusters reside. The velocities involved are measured in hundreds or a few thousand kilometers per second, but the distances are so large that the overall pattern changes only over billions of years. Clusters form where the combined gravity of dark matter and accumulated galaxies becomes strong enough to bind the system against the general expansion of the universe. Around each cluster there is a region often several million light-years across, within which the gravitational pull inward balances or overcomes the tendency of cosmic expansion to carry galaxies apart. Beyond that region, galaxies participate mainly in the smooth expansion of space, while inside it their motions are dominated by the shared gravitational field of the cluster. The positions of clusters and superclusters are mapped through several kinds of observation. Optical and infrared surveys record the light from galaxies and allow redshifts and distances to be measured. X-ray observations reveal hot gas that fills the space between galaxies in many clusters, heated to tens of millions of degrees Celsius by gravitational compression. Measurements of the gravitational lensing of more distant galaxies, whose images appear slightly distorted by the mass in the foreground, provide another way to infer the distribution of matter, including the dark matter component that does not emit light. When these observations are combined, they show that each cluster sits within a much larger dark matter halo that extends well beyond the region with bright galaxies and hot gas. Statistical tools such as correlation functions, which measure how likely galaxies are to have neighbours at a given separation, quantify the degree of clustering and provide another way to compare theory with observation. On scales of a few million light-years, galaxies are strongly clustered into groups and clusters. On scales of tens of millions of light-years, the clustering strength decreases, but remains significant, tracing the filamentary network. On scales of a few hundred million light-years and above, the correlation weakens to the point where the galaxy distribution approaches uniformity, consistent with the assumption of large-scale homogeneity. The cosmic microwave background radiation, which is the radiation remnant of the early hot phase of the universe, offers an independent view of the initial conditions for this structure. Slight variations in its temperature across the sky correspond to small differences in density in the early plasma. These variations have characteristic sizes and amplitudes that can be measured precisely and then evolve forward in time with the equations of cosmology. The same initial pattern that appears in the microwave background when evolved gives rise to a distribution of matter that resembles the observed network of filaments and clusters. This link between early time measurements and present-day structure strengthens confidence in the overall picture in which dark matter, dark energy, and ordinary matter together shape the arrangement of galaxies on large scales. From this perspective, a massive galaxy cluster hosting a bright central galaxy is one of many concentrations in the cosmic web. Each such cluster contains hundreds or even thousands of galaxies within common dark matter and hot gas. The separation between neighbouring clusters is often tens of millions of light-years, and between superclusters the distances can approach a few 100 million light-years. On yet larger scales, the pattern of clusters and superclusters blends into a nearly uniform background, and only statistical fluctuations remain. Typical galaxy clusters have total masses of many hundreds of trillions of times the mass of the Sun, most of it in dark matter, with only a small fraction in the stars and gas that emit light. The hot gas between cluster galaxies contributes a substantial share of the ordinary matter and shines mainly in X-rays, while the stars in the galaxies make up only a minor part of the total mass budget. Recognizing these proportions is important for any attempt to understand the place of a single massive galaxy and its central black hole within the wider context of cosmic structure, because the gravitational environment on large scales sets the background within which smaller systems form and evolve. On scales smaller than the full cosmic web but still extending over hundreds of millions of light-years, galaxies and clusters are grouped into superclusters and wall-like structures. A supercluster is a region in which many galaxy clusters and groups occupy a common volume and are linked by their shared overdensity relative to the cosmic mean, while remaining only weakly bound as a whole. In these regions, the combined mass of dark matter, hot gas, and galaxies produces a gravitational field that slightly slows the local expansion of space and encourages matter to stream along preferred directions. Observationally, superclusters are identified in redshift surveys as concentrations of clusters, filaments, and galaxy walls over tens to a few hundreds of millions of light-years. Within them, galaxy clusters sit in chains and knots, and voids appear as large gaps where only a few galaxies are found. One well-studied example is the structure often called the Coma supercluster, which contains the Coma cluster and the Leo cluster as its main dense components. This supercluster lies at a distance of a few 100 million light-years and spans a region measured in at least a few 100 million light-years when the positions of associated clusters and filaments are taken into account. Its total mass is dominated by dark matter, with the luminous matter in stars and hot gas contributing only a modest fraction. The Coma supercluster itself forms part of a larger feature known as the CFA Two Great Wall, an extended filament or wall of galaxies in which several rich clusters, including Coma and Leo, occupy dense nodes along a larger ridge of matter. Surveys using thousands of galaxy redshifts trace this wall as a band several 100 million light-years long, a few 100 million light-years wide, and only a few tens of millions of light-years thick. The thickness is small compared with the other two dimensions, so the system is described as a wall rather than a roughly spherical concentration. The galaxies in the wall are not arranged in a perfect sheet, but they cluster along filaments and in smaller groups and clusters embedded within the overall structure. Redshift maps display this arrangement as a web of points with enhanced density along the wall and lower density regions on either side. Analyses of these maps use algorithms that search for connected regions above a chosen density threshold to define where the wall begins and ends. Because the transition from wall to surrounding space is gradual, the exact size depends on the method and on the density level adopted, but the general picture of a long, relatively thin accumulation of matter is robust. Numerical simulations of structure formation that include dark matter and dark energy reproduce similar features with walls and filaments, forming naturally as matter flows toward dense regions along preferred directions set by the initial conditions. In such simulations, superclusters and walls are not long-lived bound objects, but transient alignments of matter that persist over long timescales without forming a single relaxed system. Observationally, the galaxies and clusters in the Coma supercluster and in the CFA 2 Great Wall show velocity patterns in which peculiar velocities, meaning deviations from pure cosmic expansion, reflect the pull of the surrounding mass distribution. Measurements of these velocities allow estimates of the mass distribution on supercluster scales, complementing information from galaxy counts and from X-ray observations of the intracluster gas in the richer clusters. Weak gravitational lensing in which the shapes of background galaxies are slightly distorted by foreground mass provides a further way to map the dark matter that outlines the wall. Combining these methods yields a consistent view in which the Coma supercluster and the CFA 2 Great Wall represent a dense segment of the large-scale structure in which multiple rich clusters, including Coma and Leo, are connected by bridges of galaxies and groups across distances far larger than the diameters of the individual clusters. In redshift space plots where one axis represents sky position and another represents distance inferred from redshift, the wall appears as an elongated concentration of points tilted across the diagram while neighbouring voids appear as relatively empty regions. The orientation of the wall in such diagrams is set by its three-dimensional geometry relative to the line of sight and does not indicate any special directionality in physical space. The existence of this structure, together with other large features such as the Sloan Great Wall and the Hercules Corona Borealis Great Wall, demonstrates that the matter distribution contains significant fluctuations in density on scales of several 100 million light-years while still approaching statistical uniformity on yet larger scales. Superclusters and walls are thus treated as high-amplitude features that stand out within the overall pattern, but they do not break the large-scale assumptions used in cosmology. Their study provides information about how matter flows on intermediate scales and about how dark matter halos of cluster size are arranged relative to one another. By comparing the abundance and sizes of observed superclusters and walls with those produced in cosmological simulations, astronomers test models of dark matter, dark energy, and the initial conditions of the universe. In this sense, the Coma supercluster and the CFA 2 Great Wall are used as laboratories for the behaviour of matter and gravity on scales larger than individual clusters, but smaller than the horizon scale set by the age and expansion rate of the universe. There are also observational limits that affect how completely superclusters and walls can be traced. Dust and gas in the plane of the Milky Way, obscure background galaxies in a zone of avoidance, where redshift surveys are incomplete and the continuity of structures across the sky is harder to follow. As a result, estimated lengths for walls such as the CFA 2 Great Wall are conservative, and the true extent may be larger than the region currently mapped. Selection effect in surveys such as magnitude limits that exclude the faintest galaxies, and incomplete sampling in some directions likewise influence how sharply the boundaries of superclusters and walls can be drawn. To minimize these biases, surveys combine data from multiple telescopes and wavelengths, and analysis methods are tested on simulated galaxy catalogues where the true underlying structure is known. When these checks are applied, the conclusion that features such as the Coma supercluster and the CFA 2 Great Wall are genuine overdensities in the matter distribution and not artifacts of sampling becomes well supported. Within this framework, the scale defined by a supercluster or a wall marks a distinct layer in the nested hierarchy of cosmic structure, larger than individual clusters and filaments, but still much smaller than the full region over which the universe can be treated as statistically uniform. A galaxy cluster is a gravitationally bound collection of many galaxies embedded in a common halo of dark matter and immersed in a volume of hot gas that emits strongly in X-rays. The Leo cluster, also catalogued as Able 1367, is one such system. It lies in the direction of the constellation Leo at a distance of a few 100 million light-years, corresponding to a modest redshift typical of nearby rich clusters. Surveys that map the positions and redshifts of galaxies show that this cluster contains at least several dozen large galaxies and roughly 100 significant members when fainter systems are included concentrated within a region a few million light-years across. The cluster is part of the Coma supercluster and contributes together with the Coma cluster to the mass concentration that defines this supercluster. In redshift surveys, galaxies identified as members of the Leo cluster have line-of-sight velocities that cluster around a common value with a spread of several hundreds of kilometers per second. This spread or velocity dispersion reflects the depth of the gravitational potential well defined by the combined mass of dark matter, galaxies and intracluster gas. Studies that combine velocity data with simple dynamical models estimate a total mass of several 100 trillion times the mass of the Sun for the Leo cluster, placing it among the richer nearby clusters, although still somewhat less massive than the Coma cluster. The distribution of galaxies within the Leo cluster is not completely relaxed or symmetric. Optical imaging and spectroscopy show at least two main concentrations often described as northwest and southeast subclusters, with galaxies in each component sharing similar velocities and spatial positions. This arrangement, together with evidence from the intracluster gas, indicates that the system is dynamically young, and that the subclusters are in the process of merging along a preferred axis across the cluster. The intracluster medium, which is the diffuse gas that fills the volume between cluster galaxies, is observed in X-rays. For the Leo cluster, this emission has a luminosity characteristic of moderately rich clusters and a temperature corresponding to gas heated to several tens of millions of degrees Celsius. X-ray images reveal that the emission is not perfectly smooth. Instead, there are clumps and enhancements associated with individual galaxies and with substructures in the cluster. Some of these enhancements correspond to galaxies that are losing gas through ram pressure stripping, while others appear as isolated clouds of hot gas without clear optical counterparts, indicating that the cluster environment can remove and rearrange gas independently of the stellar components. The galaxy population of the Leo cluster is notable for a relatively high fraction of spiral and irregular galaxies, compared with many other rich clusters at similar distances, which are often dominated in their central regions by elliptical and lenticular galaxies. Statistical studies of the cluster membership classify it as spiral-rich, with many late-type galaxies showing evidence of ongoing or recent star formation. At the same time, there is also a substantial population of early-type galaxies, especially near the densest parts of the cluster. This mixture suggests that environmental processes that transform spirals into lenticulars and ellipticals are active but not yet complete across the system. Indicators of such processes include truncated gas disks, asymmetric gas distributions, and ionized gas tails extending away from some galaxies interpreted as signs of interactions with the intracluster medium and with the cluster gravitational field. Dynamical analyses use the positions and velocities of member galaxies to infer the structure of the cluster in 3 dimensions. In the Leo cluster, the velocity distribution departs from a simple Gaussian form, supporting the view that the system is not fully virialized, and that subclusters with distinct infall histories are present. The inferred region of influence within which the cluster potential significantly alters galaxy motions relative to the general cosmic expansion extends to several megaparsecs in radius, encompassing not only the dense core, but also an infall region, where galaxies are still moving inward for the first time. In this broader region, filaments and groups feed galaxies and gas into the main cluster body. Some of the infalling galaxies are already affected by the dense intracluster medium, showing long streams of stripped gas that trail behind them as they move at high speed through the cluster. X-ray and optical line emission from these tails provide direct evidence of interaction between galactic gas and the ambient medium. At the same time, isolated multiphase gas clouds within the cluster volume observed in X-rays, optical emission lines, and molecular emission illustrate that strip material can persist as coherent structures for extended periods while mixing gradually with the surrounding hot gas. Together, these observations build a coherent view of the Leo cluster as a massive, dynamically young system with significant substructure, a complex intracluster medium, and a diverse galaxy population, all confined within a common gravitational well defined by a large dark matter halo. A galaxy cluster environment is described not only by its total mass and intracluster gas, but also by the detailed properties of the galaxies that share the same gravitational potential. In the Leo cluster, the projected positions of member galaxies on the sky and their measured redshifts allow astronomers to build catalogues of systems that are highly likely to be physically bound to the cluster, rather than lying in the foreground or background. When the distribution of confirmed members is plotted, the result is a pattern in which galaxies crowd most densely near the center of the cluster and gradually thin out toward the edges of the region where the cluster potential dominates. Within a characteristic radius of a few million light-years, the projected surface density of galaxies declines roughly monotonically, with distance from the center, though local overdensities associated with subclusters and infalling groups are clearly visible. In the densest regions, the typical separation between bright galaxies is measured in only a few 100,000 light-years, while in the outskirts it grows to several times that value. This variation in number density and typical separation is an important control on how often galaxies interact directly and how strongly each system experiences the combined tidal field of its neighbors and of the cluster as a whole. Morphological classifications based on optical imaging divide the galaxy population into ellipticals, lenticulars, and spirals, with smaller irregular systems included among the fainter members. In the central parts of the Leo cluster, as in many rich clusters, early type galaxies dominate the brightest end of the luminosity function. Large ellipticals and lenticulars with smooth light profiles and little or no visible ongoing star formation occupy the highest density regions, often near the centers of subclusters. Farther from the center and in lower density regions such as the infall zone, and along connecting filaments, the fraction of spirals increases. These spirals frequently show structured disks, spiral arms, and star-forming regions traced by blue light and by emission lines from ionized gas. The change in morphological mix with local galaxy density illustrates a general trend observed in many clusters in which dense environments favour early-type systems, while more isolated regions retain a higher proportion of star-forming spirals. Spectroscopic observations provide additional information beyond morphology. For each galaxy, spectra measure the average age of the stellar population, the current star formation rate, and the presence of gas inflows or outflows. In the Leo cluster, many spirals display signs of disturbed gas disks, asymmetric line emission, or truncated star-forming regions, suggesting that interaction with the surrounding medium has begun to alter their evolution. Some show enhanced central star formation that may be triggered by tidal interactions while their outer disks are depleted of gas. Early-type galaxies, by contrast, typically exhibit older stellar populations with little current star formation and smoother kinematics dominated by random stellar motions rather than ordered rotation. These distinctions map onto environmental measures such as projected cluster-centric distance and local galaxy surface density, reinforcing the link between environment and galaxy properties. Beyond the broad categories of morphology and star formation, the velocities of galaxies within the cluster yield further insight into how different subpopulations occupy phase space, meaning the combined space of positions and velocities. By plotting line-of-sight velocity against projected distance from the cluster center, astronomers identify structures such as caustics that outline the region where galaxies are gravitationally bound, as well as substructures associated with infalling groups. Spiral-rich subgroups often appear with slightly distinct mean velocities, or with coherent patterns that indicate that they have not yet fully mixed into the cluster potential. More evolved early-type populations are more smoothly distributed in both position and velocity, consistent with longer residence times in the cluster. This difference suggests that the present-day mix of galaxies reflects several stages of accretion, with some systems having spent many billions of years in the cluster and others having entered more recently along filaments or in groups. Environmental processes that act on galaxies in the cluster can be grouped broadly into gravitational mechanisms and interactions with the intracluster medium. Gravitational processes include tidal stripping, in which the outer parts of a galaxy are pulled away by the tidal field of the cluster, or by close passages with other galaxies, and galaxy harassment, in which repeated high-speed encounters gradually heat and thicken disks and drive gas toward the center. Encounters and mergers between galaxies are less common at the high relative velocities typical of rich clusters than in small groups. But when relative velocities and impact parameters are favorable, mergers do occur and can transform morphology and star formation histories. Interactions with the intracluster medium are often dominated by ram pressure stripping, in which the hot diffuse gas exerts a pressure on the interstellar medium of a galaxy moving rapidly through it. When this pressure exceeds the restoring gravitational force that holds gas in the galactic disk, gas is removed, leading to tails and wakes of stripped material. Observations of the Leo cluster reveal several galaxies with long tails of ionized gas, or X-ray emitting plasma that trace this process. Over time, ram pressure stripping and related hydrodynamic mechanisms can remove significant fractions of a galaxy gas reservoir, shutting down star formation and altering its appearance from a gas-rich spiral to a gas-poor, more quiescent system. Statistical comparisons of galaxy properties as a function of environment within the cluster, such as star formation rates versus local density, or gas content versus projected radius, quantify the cumulative impact of these processes. In the Leo cluster, these mechanisms operate over timescales of many billions of years, gradually reshaping the mix of galaxy types found at different radii and densities within the common potential well. The resulting radial gradients in morphology, gas content, and star formation activity provide a direct observational record of long-term environmental influence within a single cluster scale system. These gradients are measured with well-established statistical methods applied to large samples of member galaxies. Within the Leo cluster, the galaxy NGC 3842 stands out as the brightest and one of the most massive stellar systems. It is classified as a giant elliptical galaxy with a smooth light distribution that lacks the prominent spiral arms and dust lanes seen in late-type galaxies. Imaging surveys measure its projected size on the sky as roughly 1.5 arc-minutes by about 1 arc-minute. At a distance of a few hundred million light-years, this corresponds to a physical diameter of order 100,000 light-years, comparable to or somewhat larger than the stellar disk of the Milky Way, but with a very different internal structure. Photometric studies show that its radial light profile is well described by a high-index Sersic law similar to a de Vaucouleurs profile in which the surface brightness declines steadily with radius without a sharp outer edge. The half-light radius, meaning the radius that encloses half of the total measured light, lies at several tens of thousands of light-years from the centre, indicating a very extended stellar envelope. The total luminosity in the visual band places NGC 3842 among the most luminous galaxies in the nearby universe, with an absolute magnitude significantly brighter than that of the Milky Way or of typical large spirals. When this luminosity is combined with reasonable estimates of the stellar mass-to-light ratio for an old metal-rich stellar population, the implied stellar mass lies in the range of a few hundred billion to around 1 trillion times the mass of the Sun. This estimate depends on the assumed mass-to-light ratio and on details of the initial mass function used to describe the distribution of stellar masses, but it is consistent with NGC 3842 being a very massive elliptical system. Spectroscopic observations of its integrated light show that the stellar population is dominated by old stars with relatively high metallicity, meaning that the gas from which they formed had already been enriched by earlier generations of supernova explosions. The optical colours are correspondingly red with little evidence for recent or ongoing star formation. Emission lines that would indicate strong current star-forming activity are weak or absent in typical spectra of the main body of the galaxy. The stellar kinematics measured through absorption line broadening reveal a central velocity dispersion of several hundred kilometers per second, a value that is characteristic of giant ellipticals and supports the high dynamical mass inferred from photometry. At larger radii, the velocity dispersion profile reflects a combination of the galaxy potential and the surrounding cluster environment, with some studies indicating a gradual change as the contribution from the cluster, dark matter halo, becomes more important. The position of NGC 3842 within the Leo cluster is close to the region of highest galaxy surface density and near the peak of the intracluster X-ray emission, although detailed dynamical analyses suggest that it does not lie exactly at the center of mass of the full cluster dark matter distribution. Even so, it functions observationally as the brightest cluster galaxy, meaning that it dominates the light in its immediate vicinity and serves as a convenient reference point for mapping the cluster. Deep imaging reveals several neighboring galaxies within a small projected radius, including somewhat fainter ellipticals and spirals, but these companions contribute only a small fraction of the total luminosity within the central region, compared with NGC 3842 itself. The galaxy also hosts a rich system of globular clusters that extend far into its halo. Counts of these clusters in wide-field images indicate a population numbering in many thousands, with a spatial distribution that is more extended than the starlight of the main body. The colours of the globular clusters show a bimodal pattern, with metal-poor clusters that are bluer and metal-rich clusters that are redder, as is commonly seen in massive ellipticals. The metal-rich clusters tend to be more centrally concentrated, while the metal-poor clusters trace the outer halo and may connect to the cluster-scale environment. This globular cluster system provides additional traces for the gravitational potential at large radii and offers clues to the assembly history of the galaxy through accretion and mergers. Surface brightness measurements at very low levels show that the envelope of NGC 3842 blends gradually into the diffuse intracluster light, which is the faint glow produced by stars that are no longer bound to any single galaxy. This transition is not sharp, and different definitions of the galaxy boundary can yield slightly different effective sizes and luminosities. Nevertheless, the central regions where the surface brightness is highest are clearly dominated by stars gravitationally bound to NGC 3842. In terms of structural parameters such as luminosity, effective radius, central surface brightness and velocity dispersion, NGC 3842 lies at the bright and massive end of the empirical relations that describe early type galaxies, including the fundamental plane that links size, surface brightness and kinematics. Its properties are broadly consistent with expectations for a brightest cluster galaxy, formed through repeated mergers and accretion events within a dense environment which would naturally produce a large, slowly rotating or mildly rotating stellar system with an extended envelope and an old metal-rich stellar population. In observational classification schemes that rank cluster galaxies by luminosity and morphology, NGC 3842 is therefore identified as the dominant elliptical in Obol 1367, and as the primary contributor to the optical appearance of the cluster core. Within the Leo cluster, the galaxy NGC 3842 can be described more precisely in terms of its internal structure and light distribution. Deep imaging in several optical bands records its surface brightness down to very low levels, allowing the stellar envelope to be traced to large radii. When isophotes, meaning contours of equal surface brightness, are fitted to the image, they appear nearly elliptical over a wide range of radii, with only modest changes in ellipticity and position angle. This behavior indicates that the projected shape of the galaxy on the sky is smooth and only mildly flattened without strong twists or asymmetries that would signal recent major disturbances. The axis ratio inferred from the isophotes suggests that the three-dimensional shape is likely triaxial, as is common for giant ellipticals, but the exact intrinsic geometry cannot be determined uniquely from projection alone. The radial surface brightness profile averaged over isophotes follows a Circic type form with a high index, which means that the profile is steep in the inner regions and has an extended outer wing without a sharp truncation. At small radii, the intensity rises rapidly toward the centre, while at large radii it falls off gradually over many tens of thousands of light years. The half-light radius, defined by the radius that encloses half of the total integrated light, lies at several tens of thousands of light years, and serves as a convenient scale length for comparing NGC 3842 with other early type galaxies. When placed on diagrams that relate effective radius, surface brightness, and stellar velocity dispersion, the galaxy occupies a location consistent with the upper end of the fundamental plane relation. Multiband photometry shows that the integrated colours of NGC 3842 are relatively red, and that there is a mild but measurable colour gradient with radius. The central regions appear slightly redder than the outskirts, a pattern that is usually interpreted as a metallicity gradient in which stars near the centre tend to have higher heavy element abundances than those farther out. Spectral indices derived from absorption features in integrated light spectra support this picture, indicating older, more metal-rich populations in the inner zones and somewhat lower metallicity at larger radii, while the mean stellar ages remain high throughout. The presence of such gradients implies that star formation and assembly were not perfectly uniform across the galaxy, but instead proceeded in ways that left lasting radial differences in chemical composition. Structural decompositions that attempt to represent the galaxy light as the sum of distinct components sometimes use a combination of an inner component and an extended outer envelope. In these models, the inner part dominates the light within a few effective radii, while the outer component contributes a larger share of the light at low surface brightness levels. The outer envelope often shows a smoother connection to the diffuse intracluster light, suggesting that stars in this region may have originated in disrupted satellites or in material tidally stripped during past mergers. Regardless of the exact decomposition method, the observational fact is that NGC 3842 maintains detectable stellar light well beyond the radius where a typical spiral disk would fade into the halo, and that this light is smoothly distributed rather than confined to discrete streams at current observational limits. Kinematic measurements complement the photometric picture. Long-slit and integral field spectroscopy across the face of the galaxy measure the line-of-sight stellar velocity distribution as a function of position. For NGC 3842, the mean rotation is modest compared with the random motions of stars, so the system is classified as a slow rotator in the framework used for early-type galaxies. The velocity field shows only gentle gradients, while the velocity dispersion remains high over a broad range of radii before declining gradually at larger distances from the center. The combination of high dispersion and low rotation indicates that the stellar orbits are mostly disordered rather than confined to a thin rotating disk. Higher order moments of the line-of-sight velocity distribution, such as skewness and kurtosis, provide further constraints on the orbital structure, allowing dynamical models to infer the balance between radial and tangential orbits as a function of radius. In massive ellipticals such as NGC 3842, these analyses often find a mix of orbit families consistent with a triaxial potential. At large radii well beyond the half-light radius, planetary nebulae and globular clusters associated with the galaxy serve as additional traces of the gravitational potential. Their velocities can be measured individually and extend the kinematic information to distances where the surface brightness of the diffuse light is too low for reliable integrated spectroscopy. In NGC 3842, the spatial and velocity distributions of globular clusters indicate that the gravitational potential continues to rise with radius, in a manner consistent with a massive dark matter halo that envelopes the stellar body. The transition from a regime dominated by the stellar mass of the galaxy to one where dark matter contributes the majority of the gravitational field occurs over radii of many tens of thousands of light-years. Observations of X-ray emitting gas associated with the galaxy halo provide an independent cross-check on this mass distribution, since the temperature and density profiles of the hot gas must satisfy hydrostatic equilibrium in the combined potential of stars and dark matter. When these different data sets are interpreted together with dynamical models, the resulting mass profile supports the picture of NGC 3842 as a very massive extended elliptical with a smooth stellar structure embedded within a large dark matter halo. When structural parameters such as effective radius, central velocity dispersion, and surface brightness are compared statistically with those of massive disk galaxies, like the Milky Way NGC 3842 occupies a regime of larger size, higher dispersion, and weaker net rotation. It is a characteristic example of growth through mergers and accretion in a dense environment with a smooth extended stellar body that is dynamically hot over most of its volume. The motions of stars within NGC 3842 provide a direct measure of the gravitational field generated by its stars, dark matter, halo, and surrounding environment. Spectroscopic observations with long slits and integral field units record the absorption line spectra of the galaxy at many positions across its face. By comparing the observed absorption features with those of template stellar populations, astronomers determine the line-of-sight velocity distribution of the stars at each location. The mean velocity shows how different regions move toward or away from the observer while the width of the distribution expressed as a velocity dispersion reflects the range of stellar speeds around that mean. In NGC 3842, the central line of sight velocity dispersion is measured to be several hundred kilometers per second, a value typical of the most massive elliptical galaxies. As one moves outward from the center along the major and minor axes, the velocity dispersion profile declines gradually, but remains high over a large fraction of the luminous body before dropping more noticeably at the largest radii that can be probed with good signal-to-noise. The rotation field is modest, with relatively small differences in mean velocity between opposite sides of the galaxy, compared with the large random motions inferred from the dispersion. This pattern indicates that pressure support from random stellar motions rather than ordered rotation carries most of the load in balancing gravity. To characterize the velocity distribution in more detail, analyses often expand it in a series of Gauss-like functions and measure higher-order moments that describe deviations from a simple Gaussian shape. Skewness parameters quantify whether there is an excess of stars on the high-velocity side in a given direction, while kurtosis-like measures indicate whether the distribution has broader wings than a Gaussian. In NGC 3842, the values of these higher-order terms are consistent with a mix of radial and tangential orbits in a triaxial potential, rather than with a system dominated by a single orbit family. This information helps to reduce degeneracies when constructing dynamical models, because different combinations of mass profile and orbital structure can in principle reproduce the same basic dispersion profile. To translate the kinematic measurements into a mass profile, dynamical models are constructed. In one common approach, the galaxy is represented as a superposition of many stellar orbits in a trial gravitational potential. The weights of these orbits are adjusted until the model reproduces the observed surface, brightness distribution, and the measured line of sight velocity distributions at all sampled positions. The resulting model then yields an estimate of the total mass enclosed within each radius, and of the relative contributions from stars and dark matter, given an assumed stellar mass-to-light ratio. In NGC 3842, such orbit-based models favor a stellar mass-to-light ratio consistent with an old metal-rich population, and require a dark matter component that becomes increasingly important beyond several tens of thousands of light years. Within the inner regions, inside roughly 1/2 light radius, the stellar mass dominates the gravitational potential, and the total enclosed mass scales approximately with the integrated light. As the radius increases, the mass inferred from the kinematics grows faster than would be expected from the stars alone, indicating the presence of a dark matter halo with a more extended distribution. This dark matter component is usually described with parametric profiles motivated by numerical simulations of structure formation, in which the density falls off with radius more slowly than that of the stars. Fits to the stellar kinematics combined with constraints from the number and velocities of globular clusters at large radii show that the total mass within a radius of order 100,000 light-years is several times larger than the stellar mass inferred from photometry, implying that dark matter contributes a substantial fraction of the total. Beyond this radius, the contribution from the host cluster potential also begins to play a role, and the transition from galaxy-dominated to cluster-influenced dynamics is gradual rather than sharp. Additional information about the mass profile comes from X-ray observations of hot gas associated with the galaxy halo. If this gas is approximately in hydrostatic equilibrium, meaning that pressure gradients balance gravity, its temperature and density profiles encode the gravitational acceleration as a function of radius. For a massive elliptical like NGC 3842, the gas temperature of several tens of millions of degrees Celsius and its spatial distribution are consistent with a deep potential well. When mass profiles derived from gas equilibrium are compared with those from stellar and globular cluster kinematics, the broad agreement between methods strengthens the conclusion that a massive dark matter halo surrounds the galaxy and that its influence increases with radius. Small discrepancies between methods can arise from departures from perfect equilibrium, projection effects, or limited spatial coverage, and these uncertainties are included in the quoted ranges for total mass and for the relative contributions of stars and dark matter. Studies that place NGC 3842 on empirical relations such as the Faber-Jackson relation, which links luminosity and velocity dispersion for early-type galaxies, find that its high dispersion and luminosity are consistent with expectations for a system with a very large total mass. Virial mass estimates that use characteristic radii and dispersions to infer the overall gravitational binding are likewise in line with the more detailed dynamical models. Despite the remaining uncertainties, all available kinematic indicators point toward a coherent picture in which random stellar motions act as sensitive traces of a gravitational potential that is dominated by stellar mass in the inner regions and by a massive dark matter halo at larger radii with the surrounding cluster potential gradually becoming significant toward the edge of the galaxy halo. High-resolution imaging of NGC 3842 resolves the inner kiloparsec of the galaxy and shows that its central stellar light distribution does not simply continue the steep rise of the outer Circic profile all the way to the center. Instead, the surface brightness profile flattens inside a well-defined break radius, forming what is known as a partially depleted core. In practice, this structure is quantified by fitting a core Circic model to the major axis surface brightness profile. In this model, the outer regions follow a standard Circic law, while the inner regions are described by a shallower power law, joined smoothly to the outer profile at a characteristic break radius. For NGC 3842 fits to imaging from the Hubble Space Telescope in the near-infrared band yield a break radius of a little under 1/2 of an arcsecond, together with a very shallow inner slope that indicates an almost flat central light profile. At the commonly adopted distance of a few hundred million light-years, this angular scale corresponds to a physical radius of several hundred light-years of order, 700 light-years, so the depleted core occupies a significant fraction of the inner kiloparsec of the galaxy. When the best-fitting core Circic model is compared with a hypothetical profile in which the outer Circic law is extrapolated inward without a core, the central region of NGC 3842 is found to contain less light than expected from that extrapolation. This deficit is interpreted as a stellar mass deficit, meaning that stars that might have been present if the galaxy had grown in a strictly smooth way are now missing from the very centre. The mass deficit is estimated by integrating the difference between the inward extrapolated outer profile and the observed core profile, and converting that light deficit into mass using an appropriate stellar mass to light ratio. In massive core ellipticals, including systems hosting very massive central objects, these deficits are typically on the order of 1 to a few times the mass of the central black hole, consistent with the idea that dynamical processes linked to the central mass concentration have removed stars from the inner region. The detailed structure of the core in NGC 3842 is constrained not only by the radial brightness profile, but also by the shapes of the isophotes within the inner arcseconds. Within the core radius, the isophotes remain close to elliptical and show no strong twists or irregularities, indicating that the depleted region is approximately centered on the outer galaxy, and that there are no large-scale asymmetries such as strong nuclear disks or bars dominating the light. The ellipticity is modest, and measurements of deviations from pure ellipses through higher-order Fourier terms show that the central isophotes are slightly boxy rather than strongly disk-like, in line with the behavior seen in other massive core ellipticals. This morphology supports the view that the core reflects global dynamical evolution in a triaxial stellar system rather than being the imprint of a single thin rotating structure. The extremely shallow inner slope measured for NGC 3842 means that over a substantial fraction of the core radius, the surface brightness changes only slowly with radius, so the three-dimensional stellar density rises toward the center much less steeply than in galaxies without depleted cores. Observational work on samples of core ellipticals with well-measured central light profiles and directly measured central masses has established that the break radius of the depleted core correlates tightly with the radius over which the central mass dominates the stellar kinematic, sometimes called the sphere of influence. In these systems, the two radii are often comparable within a factor of order unity, suggesting that the processes that set the size of the core are closely linked to the region where the central mass exerts the strongest dynamical influence on nearby stars. Dynamical models and theoretical studies indicate that during the assembly of massive ellipticals, successive mergers of galaxies that already contain central massive objects can lead to the formation of binary systems. As stars pass close to such binaries, they can gain kinetic energy and be ejected to larger radii or removed from the galaxy, a process known as gravitational scouring, which naturally produces a low-density core whose size scales with the mass of the central object or objects. Empirical relations between core radius and central mass measured for galaxies with depleted cores are consistent with this picture over a wide range of masses and environments. In the case of NGC 3842, the combination of a large well-resolved depleted core, a shallow inner slope and a high central stellar velocity dispersion marks it as a typical member of the population of very massive core ellipticals in which such processes have been efficient. The core Sersic parameters place it on the same scaling relations that connect break radius, central surface brightness and spheroid luminosity for other galaxies with partially depleted cores, and dynamical modelling of its stellar kinematics independently confirms the presence of an extremely massive central object, whose mass is in the range of several billion to around 10 billion times the mass of the Sun. The detailed numerical values of the core parameters and the inferred mass deficit remain subject to uncertainties arising from the choice of model, the treatment of the point spread function, and the adopted distance. But across these variations, the basic observational facts are robust. NGC 3842 has a resolved partially depleted stellar core with a characteristic radius of several hundred light-years, a very shallow inner light profile and structural parameters that fit smoothly into the broader population of core ellipticals in dense environments. Supermassive black holes are compact objects with masses in the range from roughly 1 million to many billions of times the mass of the Sun that reside at the centers of galaxies and generate strong gravitational fields in their immediate surroundings. In current astrophysical models, they are treated as standard components of massive galaxies, particularly in systems with prominent bulges or spheroidal stellar distributions. Evidence for their presence comes from several independent observational methods that all point toward very large masses confined within very small regions at galactic centers. In nearby galaxies where individual stars or gas clouds can be resolved, the motions of these tracers provide direct constraints on the enclosed mass as a function of radius. If the mass within a small radius greatly exceeds the mass that can be accounted for by stars and gas seen in images, and if this mass is concentrated within a volume too small to be consistent with a stable cluster of stellar mass remnants, the most straightforward explanation is a central black hole with a mass in the supermassive range. The black hole at the center of the Milky Way, known as Sagittarius A star, provides a clear example. Over more than 2 decades, precise measurements of stellar orbits in its vicinity have mapped several stars that complete or nearly complete closed paths around the central object within periods of only a few decades. The orbital parameters imply an enclosed mass of a few million times the mass of the Sun within a radius of only a small fraction of a light-year. No known configuration of normal matter, can maintain such a mass in such a small volume without collapsing so a black hole is inferred. Similar, though typically less spatially resolved dynamical methods applied to other nearby galaxies use stellar absorption line kinematics or ionized gas emission lines to infer central masses. In some systems, coherent disks of water maester emission orbiting very close to the nucleus allow extremely precise measurements of rotation speeds and radii, leading to highly accurate black hole mass estimates. Beyond the local volume, direct resolution of individual orbits is not possible, but the general principle remains the same. The presence of a central massive object is inferred from how stars and gas move under its gravitational influence. For galaxies like NGC 3842, three-dimensional dynamical modeling of stellar kinematics across the inner region is used to measure the mass of the central black hole. The models incorporate the observed surface brightness distribution, an assumed stellar mass-to-light ratio, and a trial central mass. By adjusting the orbital structure and the black hole mass to fit the observed velocity field and dispersion profile, astronomers recover a range of allowed masses for the central object. For NGC 3842, this procedure yields a black hole mass in the range of several billion to roughly 10 billion times the mass of the Sun, making it one of the more massive central black holes measured through stellar dynamics in a nearby galaxy. Other well-studied massive galaxies, such as the giant elliptical in the Virgo cluster, known as Messier 87, and the central galaxy NGC 4889 in the Coma cluster, host central black holes whose masses are of the order of several billion times the mass of the Sun measured through combinations of stellar dynamics, gas dynamics, and in the case of Messier 87 high-resolution imaging of the immediate environment around the event horizon. These systems together define the upper mass end of the population of central black holes known in the nearby universe through spatially resolved methods. At lower masses, galaxies with small bulges or low-mass spheroids host central black holes with masses from a few million to a few 100 million times the mass of the Sun, again inferred from stellar or gas kinematics where possible, and from indirect methods in more distant objects. Indirect methods become necessary when spatial resolution is insufficient to resolve the sphere of influence of the black hole, meaning the region within which its gravity dominates over that of the surrounding stars. In active galactic nuclei, where the central black hole accretes gas at a significant rate variability in the continuum emission, and in the broad emission lines provides a way to estimate the size and characteristic velocity of the gas in the broad line region. Techniques such as reverberation mapping measure the time delay between changes in the continuum source and the response of the line emitting gas, yielding a characteristic radius, while the widths of the emission lines indicate characteristic velocities. When combined, these quantities give an estimate of the central mass under the assumption that the gas motions are dominated by gravity. Large samples of such measurements have established correlations between black hole mass and readily observable quantities such as bulge luminosity, bulge stellar mass, and stellar velocity dispersion. These scaling relations, often summarized as relations between black hole mass and spheroid properties, imply that the growth of central black holes and the assembly of galactic bulges are linked processes. For a given galaxy, the mass predicted by these relations can be compared with a direct dynamical measurement if one is available. In the case of NGC 3842, the directly measured black hole mass lies at the high end of or somewhat above the range, predicted by standard scaling relations for galaxies of its luminosity and velocity dispersion. This outcome is consistent with the general observation that the most massive central black holes are often found in the most luminous, brightest cluster galaxies, and that such systems tend to occupy the upper envelope of the black hole mass versus host property relations. The uncertainties in both the dynamical mass measurements and in the calibration of the scaling relations mean that some discrepancy between predicted and measured values is expected, and current data for NGC 3842 are compatible with a black hole mass of several billion to roughly 10 billion solar masses within these uncertainties. Across the full population of galaxies studied so far, the presence of central massive black holes appears to be nearly universal in systems with substantial bulges, with only a minority of cases showing stringent upper limits that rule out black holes above a few 100,000 solar masses. Observational selection effects mean that low-mass black holes in small galaxies are harder to detect, so the census at the low-mass end remains incomplete. At the high-mass end, where NGC 3842 resides, the combination of large black hole mass, high central stellar velocity dispersion, and the presence of a resolve-depleted core marks it as a typical example of the class of galaxies in which central black holes reach extreme masses and strongly influence the structure and dynamics of the inner regions. The measurement of the mass of the central black hole in NGC 3842 relies on stellar dynamical modelling that combines high-resolution imaging with spatially resolved spectroscopy of the inner regions of the galaxy. High-quality images from space-based and large ground-based telescopes provide the two-dimensional distribution of starlight down to small radii, including the partially depleted core described previously. This surface brightness map is deprojected under plausible assumptions about the three-dimensional shape of the galaxy to yield a stellar luminosity density as a function of radius. An assumed stellar mass-to-light ratio then converts this luminosity density into a stellar mass density profile. In parallel, long slit and integral field spectroscopic observations along several position angles across the central region measure the line of sight velocity distribution of the stars in many spatial bins. For each bin, the mean velocity, velocity dispersion, and higher order shape parameters are extracted from the spectra. These kinematic measurements sample radii that extend from well inside the core region out to distances of several kiloparsecs, thereby covering both the zone where the central black hole has a strong influence and the region where the stellar mass of the galaxy dominates. The modelling task is to find a gravitational potential that is consistent with both the observed light distribution and the measured kinematics. In the widely used orbit superposition method, also known as Schwarzschild modelling, a trial gravitational potential is specified by choosing values for the stellar mass-to-light ratio, the parameters of the dark matter halo, and the mass of the central black hole. Within this potential, a large library of stellar orbits is computed that spans the relevant ranges of energy and angular momentum. Each orbit contributes a known amount of light and kinematic signal to each spatial bin when projected along the line of sight. By assigning non-negative weights to these orbits and adjusting those weights, the modeler seeks a superposition that reproduces the observed surface brightness and the full line of sight velocity distribution at all measured positions. This procedure is repeated over a grid of trial black hole masses and mass-to-light ratios. For each trial, the quality of the match between model and data is quantified by a goodness of fit statistic. The range of black hole masses that produce acceptably good fits, given the observational uncertainties, then defines the allowed mass interval. In NGC 3842 models that emit a central black hole, or that include only a small central mass, fail to reproduce the observed steep rise in velocity dispersion toward the center and the detailed shapes of the central line of sight velocity distributions. As the assumed black hole mass is increased, the fit to the inner kinematics improves up to a point where further increases do not yield significant improvements and may begin to worsen the fit at some radii. The optimal models for standard assumptions about the stellar mass-to-light ratio and dark matter halo structure favour a black hole mass of order 10 billion times the mass of the Sun, with an allowed range that extends from several billion to somewhat above 10 billion solar masses once systematic uncertainties are included. Important sources of uncertainty include the distance to the galaxy, which sets the physical scale corresponding to a given angular radius, the assumed stellar mass to light ratio, which can vary with the detailed properties of the stellar population, and the possible presence of gradients in that ratio with radius. Additional uncertainties arise from the limited spatial resolution of the spectroscopic data, which blends information from different radii within each spatial element, and from the assumption that the galaxy is in a steady state that can be represented by a time-independent orbital superposition. Modeling tests that explore different dark matter halo parameterizations, different orbital anisotropies, and alternative deprojections of the light distribution are used to estimate how robust the inferred black hole mass is to these choices. In practice, while such variations do shift the best-fitting mass by amounts comparable to the formal statistical errors, the conclusion that the central black hole has a mass of several billion solar masses or more remains stable across a wide range of plausible model assumptions. Another way to characterize the influence of the central mass is to compute its sphere of influence, defined approximately as the radius within which the gravitational potential of the black hole dominates over that of the surrounding stars. This radius can be estimated by equating the enclosed stellar mass to the black hole mass, or in a simplified form by comparing the characteristic gravitational acceleration of the black hole at a given radius with the characteristic motions of stars in the host galaxy. For a black hole mass of order 10 billion solar masses and a typical central stellar velocity dispersion of several hundred kilometers per second, the corresponding sphere of influence radius is of order a few hundred light years. This scale is comparable to the size of the depleted stellar core measured in NGC 3842, which supports the picture in which the presence and growth of the central black hole are linked to the formation of the core through dynamical processes that operate within this radius. Because the angular size of the sphere of influence at the distance of the Leo cluster is only a fraction of an arc-second resolving, it requires high spatial resolution and careful treatment of the effects of atmospheric blurring and instrumental optics on the observed spectra. The observational data used for the mass measurement therefore combine seeing limited spectroscopy from large telescopes with the fine spatial sampling and stable point spread function of space-based imaging. Together, these data and the accompanying dynamical models yield one of the more secure very high mass estimates for a central black hole in a nearby galaxy, and they demonstrate that stellar dynamics can measure black hole masses well into the upper end of the observed mass distribution when spatial resolution and data quality are sufficient. Scaling relations between the masses of central black holes and the properties of their host galaxies provide an important context for interpreting the mass of the object in NGC 3842. Observational studies of large samples of nearby galaxies show that the mass of the central black hole correlates with the luminosity and stellar mass of the spheroidal component, often referred to as the bulge, and with the stellar velocity dispersion measured in the central regions. In practice, these relations are established by collecting galaxies for which black hole masses have been determined through stellar dynamics, gas dynamics, maser dynamics, or reverberation mapping, and then fitting functions that describe how the logarithm of the black hole mass changes with the logarithm of the host property. Although the details of the functional form and the exact coefficients depend on the sample and fitting method, the general result is that more massive, more luminous, and higher dispersion spheroids host more massive black holes. The scatter around these relations is significant, typically corresponding to factors of a few, in mass at fixed host property, which means that any single galaxy can lie above or below the mean prediction without conflicting with the overall trends. Within this framework, NGC 3842 is first characterized by its stellar velocity dispersion and total luminosity, its central dispersion of several hundred kilometers per second, and its high luminosity place it at the upper end of the distributions for nearby early type galaxies. If one applies a standard relation between black hole mass and stellar velocity dispersion, the predicted mass for a galaxy with the dispersion of NGC 3842 is of order a few billion times the mass of the Sun. A relation between black hole mass and bulge stellar mass or luminosity yields a similar characteristic scale. These predicted values are already large compared with the masses of black holes in galaxies like the Milky Way, where Sagittarius A star has a mass of only a few million times the mass of the Sun, but they are somewhat lower than the direct dynamical measurement for NGC 3842, which indicates a mass closer to around 10 billion times the mass of the Sun. In other words, the directly measured mass for this galaxy lies toward the upper envelope of the black hole mass distribution at fixed host galaxy properties. This situation is not unique to NGC 3842. Several brightest cluster galaxies and other very massive ellipticals with well-measured central black holes show similar behavior in which the black hole mass lies above the value predicted by a straightforward extrapolation of the scaling relations, calibrated mainly on lower mass systems. Examples include the central galaxy in the Virgo cluster Messier 87, whose black hole mass inferred from stellar and gas dynamics and from imaging of the immediate environment around the event horizon is of order several billion times the mass of the Sun, and the brightest galaxy in the Coma cluster, NGC 4889, whose central black hole mass has been estimated with considerable uncertainty to be in the range of roughly 10 billion to a few tens of billions of times the mass of the Sun. In both cases, the host galaxies are among the most massive ellipticals known, and their central velocity dispersions and luminosities place them near the upper ends of the distributions for early-type galaxies, yet their black holes still appear comparatively massive even in that context. When NGC 3842 is plotted together with these galaxies, on diagrams of black hole mass versus velocity dispersion, or versus bulge mass, it occupies a position consistent with this pattern of very massive brightest cluster galaxies hosting black holes that lie on or above the upper envelope of the general relations. At the other end of the mass scale, the Milky Way and other nearby galaxies, with accurately measured central black hole masses, provide well-constrained anchors at much lower mass. Sagittarius, a star with a mass of a few million times the mass of the Sun, sits exactly where expected for a galaxy, with a modest bulge and a central velocity dispersion, far below that of a giant elliptical. Intermediate mass systems, such as normal giant ellipticals in less rich environments, tend to fall closer to the mean relations. For example, the black hole in Messier 87, although very massive, is broadly consistent with the expectations from its host properties within the observed scatter. The broader picture that emerges from these comparisons is that the mass of the black hole in NGC 3842 is extreme, but not isolated. It represents one of a class of very massive central black holes found in the brightest galaxies of rich clusters, where repeated mergers and prolonged growth of both the galaxy and its central object have produced systems at the upper end of the observed mass distributions. In quantitative terms, its black hole mass exceeds that of Sagittarius A star by a factor of roughly 1,000,000, and is comparable to or somewhat larger than the masses inferred for black holes in other well-studied giant ellipticals such as Messier 87 and NGC 4889, given the current uncertainties. The fact that NGC 3842 lies near the bright and massive end of the fundamental plane of early-type galaxies and hosts a black hole whose mass is among the highest measured through stellar dynamics makes it a key data point for testing whether the scaling relations that hold for moderate mass galaxies continue unchanged into the regime of the most massive systems, or show signs of curvature or increased scatter at the top end. In this way, NGC 3842 helps to define the observed upper scale of black hole masses in the local universe, when those masses are measured by resolved stellar dynamics rather than inferred indirectly from more distant active galactic nuclei. The gravitational sphere of influence of a central black hole is defined as the region in which its mass dominates the motions of nearby stars compared with the combined gravitational field of the surrounding stellar distribution. A common practical definition sets the radius of influence as the distance at which the enclosed stellar mass equals the mass of the black hole. Inside this radius, the potential is shaped primarily by the black hole, while outside it, the contribution from the host galaxy becomes increasingly important. For a galaxy like NGC 3842, with a central velocity dispersion of several hundred kilometers per second, and a black hole mass of several billion to roughly 10 billion times the mass of the Sun, this radius of influence is estimated to be of order a few hundred light-years. This scale is comparable to, though not identical, with the break radius of the depleted core, indicating that the central mass affects stellar dynamics over a region of similar size to the observed light deficit. Within the sphere of influence, stellar orbits respond strongly to the point-like nature of the central mass. In a purely spherical and isotropic model, the gravitational potential near the center can be approximated as that of the black hole, plus a slowly varying background term from the galaxy. In such a case, the orbital velocities at a given radius are set largely by the black hole mass, and the characteristic speed of stars rises as the inverse square root of radius as one moves inward. For the mass range inferred for the black hole in NGC 3842, the circular velocity at a radius of a few tens of light-years reaches several hundreds of kilometers per second, and at radii an order of magnitude smaller, it rises to values of order 1,000 kilometers per second. Orbital periods at these radii are correspondingly short in galactic terms, ranging from a few 100,000 to a few million years, much less than the age of the stellar population. As a result, stars within the sphere of influence complete many orbits over the lifetime of the galaxy, and their motions provide a time-averaged response to the central potential. In more realistic models that allow for anisotropic velocity distributions and triaxial shapes, the orbital structure is more complex and includes families of box orbits, tube orbits, and resonant trajectories. Even so, the presence of a dominant central mass imposes strong constraints on the allowed orbits, particularly for stars that pass close to the center. Orbits that would bring stars very near the black hole are either deflected or gradually depleted over time by processes such as gravitational scattering and, in extreme cases, tidal disruption, so the steady-state distribution function in phase space reflects a balance between orbital families that sample different regions of the central potential. The line of sight velocity dispersion profile measured in NGC 3842 encodes this influence of the central mass. In the absence of a very massive black hole, the dispersion would be expected to decrease smoothly toward the center once the innermost radii are dominated by stars on relatively circular or gently varying orbits in a slowly varying stellar potential. Instead, observations show a pronounced rise in dispersion within the inner few tenths of an arc-second, consistent with the rapid increase in orbital speeds expected in the vicinity of a compact central mass. The detailed shape of this central rise depends on the exact black hole mass, on the stellar density profile, and on the orbital anisotropy. So dynamical models that match the full, two-dimensional kinematic data can use this behavior to estimate the mass and to delineate the spatial extent of the sphere where the black hole is dynamically important. At radii just outside the sphere of influence, the gravitational contributions from the black hole and from the surrounding stars are comparable. In this transition zone, the dispersion profile is shaped by both components, and the sensitivity of the stellar motions to changes in black hole mass begins to diminish. Beyond a few times the radius of influence, the gravitational potential is dominated by the extended mass of the galaxy, and at still larger radii by the dark matter halo and the cluster environment. In that regime, changes in the assumed central mass have only a small effect on the predicted kinematics, and constraints on the black hole rely almost entirely on data obtained at radii inside or near the influence radius. The importance of resolving the sphere of influence for robust mass measurements can be quantified by comparing its angular size with the effective resolution of the observations. For NGC 3842, the estimated radius of influence corresponds to an angular scale of a few tenths of an arc-second at the distance of the Leo cluster. This scale is challenging but accessible to high-quality imaging and spectroscopy, with space-based telescopes and with large ground-based telescopes aided by good atmospheric conditions or adaptive optics. When the spatial resolution is comparable to or finer than this angular scale, the central rise in velocity dispersion and the associated changes in the full line of sight, velocity distribution, are directly sampled in several independent spatial elements. Modelling can then separate the effects of the black hole from those of the surrounding stellar mass with reasonable confidence. If by contrast the resolution were much poorer than the influence radius, the kinematic signature of the black hole would be diluted by averaging over a region where its contribution is mixed with that of the host galaxy, and the inferred mass would be more uncertain. The concept of a sphere of influence also allows comparison with central black holes in other galaxies. For Sagittarius, a star in the Milky Way, the influence radius is of order a few light years, and modern instruments resolve individual stellar orbits well within this region, enabling direct tests of gravitational theories in massive ellipticals such as NGC 3842. The influence radius is larger in absolute terms, but the greater distance means that it subtends a smaller angle on the sky, so its internal structure and stellar orbits cannot be resolved individually. Instead, integrated light spectroscopy provides ensemble averages over many stars within each spatial element. Despite this observational limitation, the same underlying definition of the sphere of influence applies, and the comparison highlights how increasing black hole mass and changing host galaxy properties shift the characteristic physical scale of the region where the central mass dominates. In NGC 3842, the combination of a large estimated radius of influence, a resolved depleted core of similar size and high central velocity dispersion, establishes a consistent picture in which stellar motions inside a region of several hundred light-years are governed primarily by the gravitational field of the central black hole, with the contribution from the surrounding stellar body becoming gradually more important with increasing radius. The event horizon of a black hole is defined in general relativity as the boundary in space beyond which light and matter cannot return to the external universe. For an isolated, non-rotating black hole in otherwise empty space, the radius of this boundary, often called the Schwarzschild radius, depends only on the mass of the black hole and increases in direct proportion to that mass. This proportionality means that if the mass is multiplied by some factor, the event horizon radius is multiplied by the same factor. In practice, it is convenient to express black hole masses in units of the mass of the Sun, and distances either in kilometers in astronomical units or in light travel times. For each solar mass of a non-rotating black hole, the corresponding Schwarzschild radius is a few kilometers. For a black hole with a mass of many billions of solar masses, the Schwarzschild radius therefore reaches many billions of kilometers and can also be expressed as a distance that light takes a significant fraction of a day to cross. The stellar dynamical measurements for NGC 3842 indicate a central black hole whose mass is of order several billion to roughly 10 billion times the mass of the Sun. If one adopts a representative value of about 10 billion solar masses for the purpose of estimating the event horizon scale, the corresponding Schwarzschild radius is of order a few tens of billions of kilometers. Light takes roughly 1 day to travel this radial distance. The diameter of the horizon measured from one side to the other through the center is therefore about 2 light days. Expressed in astronomical units, one light day is a little under 200 times the mean distance from Earth to the Sun, so the horizon radius of the NGC 3842 black hole is of order a few hundred astronomical units, and the diameter is of order several hundred astronomical units. These numbers can be compared with the size of the solar system, as defined by the orbits of the major planets, and by the region of small bodies beyond Neptune. The mean distance from Earth to the Sun is defined as 1 astronomical unit. Jupiter orbits at about 5 astronomical units, Saturn near 10 astronomical units, Uranus at about 20 astronomical units, and Neptune at roughly 30 astronomical units. The region of the Kuiper belt, populated by small icy bodies, extends from just beyond Neptune to distances of a few tens of astronomical units. Farther out the region, where long-period comets are thought to originate, often referred to as the Oort cloud, may extend to distances of many thousands of astronomical units, although its detailed structure is still uncertain and not directly mapped. Against this context, horizon radius of a few hundred astronomical units implies that if the black hole in NGC 3842 is hypothetically placed at the location of the Sun, the event horizon extends well beyond the orbits of all the major planets and encloses the inner part of the region where Kuiper belt objects reside. All planetary orbits and small body populations out to that radius lie inside the horizon. From the perspective of physical scale, this means that the boundary beyond which light cannot escape for this black hole has a diameter that is large compared with the planetary region of the solar system, but small compared with the full extent of the distant comet reservoir. Another useful comparison is with the event horizon of the black hole in the centre of the Milky Way Sagittarius A star. For a given black hole mass, the Schwarzschild radius scales directly with that mass, so the ratio of horizon radii between two black holes is equal to the ratio of their masses. Sagittarius A star has a mass of a few million times the mass of the Sun, whereas the central object in NGC 3842 has a mass of several billion to around 10 billion solar masses. The mass ratio is therefore of order a few thousand, and the event horizon radius of the NGC 3842 black hole is larger than that of Sagittarius A star by the same factor. In physical terms, the Schwarzschild radius of Sagittarius A star is only a few million kilometers, corresponding to a light crossing time of well under 1 minute, and a size comparable to that of the orbit of Mercury. By contrast, the Schwarzschild radius of the NGC 3842 black hole corresponds to a light crossing time of about 1 day, and a size hundreds of times larger than the orbital radius of Neptune. When comparing with other very massive black holes measured in nearby galaxies such as the central object in Messier 87, with a mass of several billion solar masses, the NGC 3842 black hole has a somewhat larger event horizon for a given set of assumptions about spin and mass, although the differences are within factors of a few, and subject to the uncertainties in the mass determinations. What changes most strongly across the population is not the qualitative nature of the event horizon, which is the same for all non-rotating black holes in general relativity, but the absolute physical scale on which the horizon is set by the mass. For NGC 3842, that scale is in the range of a light day or so in radius, and several hundred astronomical units in diameter. This scale is much smaller than the radius of the sphere of influence, which extends over several hundred light-years, so the region where the black hole dominates stellar motions contains many nested subregions, of which the event horizon is the innermost boundary that has a direct physical meaning in the theory. As seen from Earth, the event horizon of the NGC 3842 black hole subtends an extremely small angle on the sky. At a distance of a few 100 million light-years, a physical size of a few hundred astronomical units corresponds to an angular diameter of only a fraction of a microarc second, far below the resolving power of current very long baseline interferometric arrays even at the highest radio frequencies. Direct imaging of the horizon scale as has been achieved for the black hole in Messier 87, and for Sagittarius a star is therefore not presently feasible for NGC 3842 because of its much larger distance. The size of the event horizon for this object is inferred instead from its mass through the proportionality between mass and Schwarzschild radius, together with the standard constants of general relativity, and is then expressed in terms of familiar astronomical distances to specify its physical scale, relative to structures such as planetary systems and stellar orbits. In general relativity, the region just outside the event horizon of a massive black hole is described by a curved space-time geometry in which both matter and light follow paths that differ strongly from straight lines in flat space. For a non-rotating black hole, this geometry is given by the Schwarzschild solution, in which the gravitational field depends only on the mass of the black hole and on the radial distance from its centre. In this description, the event horizon marks the radius where outward moving light can no longer increase its distance from the centre. Outside this radius, light and particles can still move outward, but their trajectories are bent by gravity, and their energy and frequency as measured by distant observers are altered in characteristic ways. For a rotating black hole, the geometry is described by the Kerr solution, which introduces additional structure such as an ergosphere and frame dragging, but the basic feature that the strength of the field increases rapidly as the event horizon is approached remains. The black hole at the centre of NGC 3842 is not directly resolved, and its spin is not measured, so analyses usually begin with the simpler non-rotating case, and then consider how rotation might shift characteristic radii inward or outward by factors of a few. In the Schwarzschild case, several radii in the near-horizon region have clear physical meanings. One is the photon orbit radius, where light can in principle travel in circular paths around the black hole. For a non-rotating black hole, this radius lies at about 1 1/2 times the event horizon radius. Circular photon orbits at this radius are unstable, so small perturbations cause photons either to fall inward across the horizon or to escape outward. Another important radius is the innermost stable circular orbit, for test particles often called the innermost stable orbit. For a non-rotating black hole, this lies at about 3 times the event horizon radius. Circular orbits outside this radius are stable against small perturbations, while those inside it are unstable. Matter slightly perturbed inward from a circular path inside. This radius cannot settle into another circular orbit, and instead spirals inward toward the horizon. In accretion disk models, this radius marks the inner edge of a geometrically thin, optically thick disk, in which gas moves on nearly circular orbits before plunging inward. For a spinning black hole, the innermost stable orbit moves inward for matter, orbiting in the same direction as the spin, and outward for matter orbiting in the opposite direction, with the exact radii depending on the dimensionless spin parameter. For the mass scale of the black hole in NGC 3842, of order several billion to roughly 10 billion solar masses, these characteristic radii correspond to large physical distances. If one adopts a mass of about 10 billion solar masses, the event horizon radius is of order a few tens of billions of kilometers as discussed previously. The photon orbit radius is then of order 1 1/2 times this value, and the innermost stable orbit radius is of order 3 times this value. Expressed in light travel times, the event horizon radius corresponds to roughly 1 day of light travel, the photon orbit radius to about 1 1/2 days, and the innermost stable orbit radius to about 3 days. In terms of astronomical units, the innermost stable orbit lies at a radius of several hundred astronomical units, so the entire region from the horizon out to this orbit occupies a radial range comparable to the planetary region of the solar system, scaled up by factors of several to a few tens. In this near-horizon region, time dilation and gravitational redshift are strong. Clocks that move on circular orbits close to the innermost stable orbit tick more slowly relative to clocks far from the black hole, and light emitted from matter near this orbit is redshifted when observed at large distances. Part of this redshift arises from the gravitational potential, and part arises from the high orbital speeds of the emitting matter, which approach a significant fraction of the speed of light near the innermost stable orbit. For a non-rotating black hole, the circular orbital speed at the innermost stable orbit is about 1/2 of the speed of light. For a black hole with significant spin, co-rotating orbits at the corresponding innermost stable radius reach even higher speeds. These high velocities and the strong curvature of space-time near the horizon lead to pronounced relativistic effects in the appearance of any luminous matter in the region, including Doppler boosting of emission from material moving toward the observer, beaming of radiation along the direction of motion, and gravitational lensing that produces multiple images and distortions of background light sources. In practice, for distant systems like NGC 3842, individual emission features from matter near the horizon cannot currently be resolved spatially, but the same physical principles apply as in closer systems, where horizon-scale imaging is possible. The gravitational field close to the event horizon also shapes the structure of any accretion flow. In simple thin disk models, gas loses angular momentum through internal stresses and slowly spirals inward on nearly circular orbits until it reaches the innermost stable radius where the disk is thought to truncate. Inside this radius, gas plunges inward on more radial trajectories and crosses the horizon on timescales of order a few orbital periods. The efficiency with which rest mass energy is converted into radiation in such disks depends on the binding energy per unit mass at the innermost stable orbit. For a non-rotating black hole, this efficiency is a little under 10%, while for rapidly spinning black holes it can be substantially higher. These values set a theoretical upper limit on the luminosity that can be produced by accretion for a given mass inflow rate. Observationally, the present accretion state of the black hole in NGC 3842 is not well constrained, and there is no strong evidence that it's currently a very luminous active galactic nucleus. The near-horizon region is therefore treated mainly through general relativistic theory, rather than through direct emission measurements. Another feature of the near-horizon geometry is the behavior of light rays that pass close to the black hole without being captured. Rays with impact parameters just above the critical value corresponding to the photon orbit radius can loop around the black hole one or more times before escaping, producing a sequence of highly demagnified, strongly lensed images of background sources. In realistic situations, these multiple loops contribute mainly to a diffuse halo of highly bent light around the black hole when integrated over many unresolved sources. The same light bending contributes to the appearance of a dark central silhouette or shadow when an optically thin emitting region surrounds the black hole, as has been seen in horizon-scale images of other systems. For NGC 3842, the angular size of any such shadow would be far below current imaging capabilities, but its physical size in kilometers or astronomical units is fixed by the mass and by the geometry of the near-horizon space-time. In summary, the near-horizon region of the NGC 3842 black hole is characterized by strongly curved space-time in which circular photon orbits the innermost stable circular orbits of matter, and the event horizon itself define distinct radial scales. Within this region, gravitational redshift time dilation and light bending are all strong orbital speeds are a substantial fraction of the speed of light, and the detailed structure and luminosity of any accretion flow are governed by general relativistic dynamics rather than by Newtonian gravity. Inside the event horizon of a black hole, the structure of spacetime is described in classical general relativity by the interior part of the same solutions that define the external gravitational field. For an idealized non-rotating black hole, this description is provided by the interior region of the Schwarzschild solution. In this geometry, the coordinate that functions as a radial distance outside the horizon changes character inside it, and takes on a role similar to that of a time coordinate, while the coordinate that labels time outside becomes more similar to a spatial coordinate. This change means that within the horizon, decreasing radius is not an option that can be avoided. Instead, it behaves like the passage of time, and all future directed paths that obey the laws of physics lead inevitably towards smaller radii. The endpoint of these paths in the classical solution is a curvature singularity at zero radius, where invariants that quantify the strength of the gravitational field, such as those constructed from the curvature tensor, diverge without bound. For a rotating black hole described by the Kerr solution, the interior structure is more complex and includes additional regions, but the basic feature that the curvature becomes extreme in an inner region remains. In both cases, general relativity treats the singularity not as a place in space, in the usual sense, but as a boundary in the mathematical description, where the theory predicts that it can no longer give finite values for physical quantities. For the black hole in NGC 3842, whose mass is in the range of several billion to about 10 billion times the mass of the Sun, the classical description of the interior follows these same equations scaled to the appropriate mass. The horizon radius sets the overall length scale of the interior region, and the curvature increases as the radius decreases toward the center. The proper time, meaning the time measured by a clock that falls freely from just inside the horizon toward the singularity, is finite and scales in direct proportion to the mass of the black hole. For an object crossing the horizon of a black hole, with the mass inferred for NGC 3842, this proper time is short, compared with the age of the galaxy or of the universe, but long compared with characteristic timescales associated with stellar mass black holes. In classical general relativity, no physical process available inside the horizon can reverse the inward progression toward the singularity or carry information back across the horizon to the external region. The causal structure of the space-time, often illustrated by conformal diagrams, shows that all future directed paths from any point inside the horizon end on the singularity, and that the horizon itself functions as a one-way boundary between the external region and the interior. The description of the interior relies on extrapolating the same equations that govern the gravitational field in regions where they have been well tested, such as the weak fields of planetary systems and the strong but not extreme fields outside the horizons of astrophysical black holes. However, the densities and curvatures near the classical singularity are far beyond those reached in any experiment or observation, and they approach or exceed the scales at which quantum effects of gravity are expected to become important. In this regime, classical general relativity is thought to be incomplete. Candidate theories of quantum gravity aim to modify or replace the behavior of space-time at very small scales, potentially altering or removing the singularity predicted by the classical theory. But at present there is no single established quantum theory of gravity with direct observational support. As a result, statements about what happens arbitrarily close to the singularity in the interior of a black hole remain theoretical and model-dependent. Observationally, the interior region inside the event horizon is inaccessible. Signals that originate within this region cannot reach distant observers, because even light is confined to paths that end at the singularity. All information about the black hole that is available to observation comes from its external gravitational field, from any radiation produced by material outside or near the horizon, and in some cases from gravitational waves generated when black holes merge. These observables test the predictions of general relativity in the domain outside the horizon and near it, but do not probe the classical singularity or any putative replacement in a quantum theory. For the black hole in NGC 3842, the existence of an event horizon and an interior region with the classical properties described by general relativity is inferred from the mass measurement, from the absence of any extended luminous central object of comparable mass, and from the success of black hole models in describing similar systems. In the standard formulation of general relativity, the external gravitational field of a stationary black hole is determined entirely by a small set of global parameters, namely mass, spin, and electric charge, a result often summarized by the statement that black holes lack additional observable structure. The interior solution corresponding to a given set of these parameters is therefore not free to vary independently. Once the mass and spin of the NGC 3842 black hole are fixed, the classical spacetime inside and outside the horizon is fixed up to coordinate transformations. The interior is treated as a region in which the curvature grows without bound as the center is approached, and in which all world lines are directed toward the singularity, while the details of the ultimate behavior at the highest curvatures are left to future theories that incorporate quantum effects in a consistent way. From the standpoint of current observations, the role of the interior solution is to provide a mathematically consistent continuation of the space-time geometry across the event horizon, ensuring that the external field of the NGC 3842 black hole fits into the broader framework of general relativity, even though the deepest interior cannot be observed directly.